Hello friends, in previous lecture we have discussed the theorems about the closed subset of complete metric space is a complete subspace. Conversely, every non-empty closed subset of complete metric space is complete, and complete subspace of any metric space is always closed. That result we have proved. In this session, we'll prove yesterday's stated theorem, which is nothing but Cantor intersection theorem. What is the statement of Cantor intersection theorem? If XD is a complete metric space and Fn is sequence of closed subsets of X satisfying two conditions. Firstly, each Fn must be non-empty set. Secondly, F1 contain, F2 contain, etc. means size of that Fn goes on decreasing. And diameter of Fn, d of Fn means diameter of Fn approaches to a zero as n tends to infinity, then intersection of Fn contains precisely 1 point. Precisely 1 point. So see the proof of this. Proof is too simple. So to find point in intersection, we have to use concept of complete metric space. Every Cauchy sequence is convergent in complete metric space. So if we are able to construct some Cauchy sequence and it is convergent, and if we are able to show that convergent limit point lies in each Fn, then we are through. Okay. So let Xn belongs to Fn for every n belongs to M. Then Xn is sequence of points. Xn is sequence of points in XD such that Xn plus 1, Xn plus 2, etc. belongs to Fn for every k greater equal m by 1. Moreover, distance between x and xm is less than equal to diameter of Fn for any nm greater than equal n greater than equal n. As xn xm belongs to Fn for every nm greater than equal n. 1. Now for given epsilon greater than 0, choose positive integer n such that 1 by n is less than epsilon. Then d of xn xm is less equal diameter of Fn one minute. Since diameter of Fn tends to 0, as n tends to infinity by 2, therefore for given epsilon greater than 0, there exists positive integer n naught such that diameter of Fn is less than epsilon minus 0. Okay. Minus 0 is less than epsilon for any n greater equal n naught. For any n greater equal n naught from 1 and 2. D of xn xm is less than epsilon for any mn greater equal n naught. What this implies is xn is Cauchy sequence in x this implies is xn is Cauchy sequence in x. Cauchy sequence in complete metric space in x. Now since xd is complete metric space, xd is complete, therefore xn is convergent. Therefore limit n tends to infinity of xn is equal to x belongs to x. It has some limit. It has some limit. Okay. This is now set 3. Now, if I take sequence xn, xn plus 1, dot etc. is subsequence of xn n equal to 1 to infinity. We such that xk belongs to fn for every k greater equal n, and therefore xn is sequence of points xn n equal to or xk k equal to 1 n to infinity is sequence of points in fn for every n. Moreover, subsequence of convergent sequence converges to same limit. Moreover, subsequence of convergent sequence has same limit, and therefore limit k tends to infinity of xk is equal to x must belongs to fn for every n. Fn closure. Okay. Fn closure. And therefore x belongs to fn for every n since each fn is closed. Fn is closed. Implies fn closure is equal to fn. And therefore x belongs to intersection of fn. X belongs to intersection of fn. Thus, intersection of fn contain at least one point. Now, if I assume that if xy belongs to intersection of fn, then d of xy 0 less equal d of xy is less or then xy belongs to fn for all n, and therefore 0 less equal d of xy less equal diameter of fn which approaches towards 0 as n tends to infinity implies d of xy must be 0. This implies d of xy must be 0, and therefore x is equal to y. So this is say 4 and this is 5. From 4 and 5, if I assume that there are 2 points in intersection of fn, then that 2 points must be equal. From 4 and 5, intersection of fn contain precisely one point, precisely single point. So thus result is proved. Converse of this result is also true. Converse of this result is also true. Now here, while proving result, in assumption we are taking each Fn to be closed set and diameter of Fn approaches towards 0. Diameter of Fn approaches towards 0. So if I delete one condition among that, then result doesn't hold. That you have to show. Means you have to construct some examples. Example. Give example of sequence of subsets, non-empty subsets of complete metric space XD, sequence of non-empty subsets Fn of non-empty subsets of complete metric space XD such that Fn contain, F2 contain, so on. F1 contain, F2 contain, and diameter of Fn tends to 0, but intersection of Fn is far. So in RU, means here I am not taking closed subsets. In RU, if I take, say, Fn set is equal to 0 to 1 by n, for every n. Take Fn is equal to, then RU is complete. First, second, F1 is equal to 0 to 1 contain, F2 is equal to 0 to half contain, dot etc. Third, diameter of Fn, which is 1 by n, approaches towards 0 as n tends to infinity, but intersection of Fn or n is equal to 5, or n equal to 1 to infinity. As n approaches towards infinity, this 1 by n approaches towards 0. 1 by n approaches towards 0. Is it right? Means it looks like says open interval 0 to 0. And therefore closeness of Fn's are required. Next example. Give example of sequence of closed subsets. Give example of sequence of closed subsets non-empty closed subsets of metric space XD such that F1 contain, F2 contain, so on, and diameter of Fn, here I am taking closed, such that contain, and intersection of Fn is equal to 5. So in complete metric space RU, Fn is equal to n to infinity is closed for each n, such that f1 contain, f2 contain, f3 contain, so on, but diameter of fn doesn't tend to 0 as n tends to infinity, and intersection of fn is phi. As n approaches towards infinity, intersection of fm become empty set. Is it clear? So now we will take the converse part of Cantor intersection theorem. Next theorem: if in matrix space xd, every decreasing sequence of non-empty closed sets, sequence fn of non-empty closed sets with diameter of fn tending to 0 as n tends to infinity, has exactly one point in intersection, then xd is complete metric space. So if I have some metric space in which whatever our sequence of closed sets where each fn is closed and size of fn goes on decreasing, means f1 contain, f2 contain, f3 dot etc., such that diameter of fn approaches towards 0 and intersection of all fn's must be singleton set, then xd must be complete metric space. Okay, so proof. As we have to show that xd is complete metric space, means we have to show that every Cauchy sequence in xd is convergent. So let xd be convergent. Let xn n equal to 1 to infinity be Cauchy sequence in metric space xd. Metric space xd. Okay. Then for given epsilon greater than 0, there exists n naught belongs to n such that d of xn xm is less than epsilon for any m greater equal n naught 1. Now take fn is equal to, I am taking, or gn set is equal to xm, xm plus 1, xm plus 2 and so on for every n. I am taking gns to be these sets. Then by 1, diameter of gn closure, we know that for any set A, diameter of A closure is always equal to diameter of B. So by using that, diameter of Gn closure is equal to diameter of Gn tends to 0 as n tends to infinity, where Gn closures are closed sets such that G1 closure contain G2 closure contain G3 closure and so on. By hypothesis, intersection of Gn closure or n contains single point x, then d of xn or xnx, is less equal diameter of Gn closure which tends to 0 as n tends to infinity, What this implies xn converges to x, and therefore x is the limit point of Gn closure. X is the limit point of Gn closure for every n. But each Gn closure is closed since each Gn closure is closed implies x belongs to Gn closure for all n. But x lies there. So d of xn converges to x. So here result is proved. Thus every Cauchy sequence in X is convergent. Thus every Cauchy sequence in XD is convergent, and therefore XD is complete matrix space. So thus we have proved converse part of finite intersection, Cantor's finite intersection theorem. So with this discussion, we'll stop our session here. Thanks for listening lecture carefully. Bye bye.